A year ago, I fixed a problem with my Proxxon milling machine. The play, or backlash, between the nut and the spindle on the x-axis had increased to a whopping 0.7 millimeters. I eliminated the wear on the spindle and made a new adjustable nut. After that, the backlash was reduced to just a few hundredths of a millimeter, and I was a happy camper. But now, the backlash on the z-axis and y-axis is starting to seriously get on my nerves. The play on the z-axis has climbed to 0.32 millimeters, and the y-axis, well, that's the one that drives me nuts with more than half a millimeter of play. I'll just turn the handwheel here until the DRO shows that the bed is moving. By comparison, the backlash on the x-axis is a real breath of fresh air, only a few hundredths of a millimeter. It's a complete case of déjà vu. I'll have to take the machine apart again to inspect the other spindles and figure out how to fix these new annoyances. And just as I'd hoped, this measurement confirms that the backlash on the x-axis is still holding up perfectly at just 32 microns. This is all the motivation I need to realize a similar fix for the other axis as well. Just recently, I built this micromill, and on it, I used spindles with trapezoidal threads and a double nut system. This allowed me to easily adjust the backlash as needed. You can see the video series about it. And even after a good amount of use, the backlash is still only around 20 microns. I think this is definitely the way to go for the bigger brother of this little guy too. Take a look at this. Right here, under the microscope, you can really see the wear on the y-axis spindle. The flanks of the M16 thread are seriously worn away. At the unused end, the thread width is a full millimeter, but here in the middle, it's just 0.8 millimeters. That's right, about 20% of the thread is already history. And since I've got the whole thing apart anyway, I might as well figure out if those wimpy little ball bearings are also contributing to the play. I'd much rather replace them with a set of 2 thrust bearings and a single ball bearing, so I can properly adjust the preload. The added 50 microns of play coming from this one is not exactly helping the situation. All right, after that depressing look at the y-axis, let's see what's going on with the z-axis, shall we? This picture doesn't quite do it justice, but the flanks of the thread inside this nut are visibly worn down. Here's the z-axis spindle under the scope. The red line shows the profile of the unused part, and that yellow area shows the wear. The damage is only on the underside, which is the pressure side of the spindle. It's not nearly as bad as the Y-axis was, but to me, it looks like it's only a matter of time before this one becomes a headache as well. Alright, I've seen enough. I've come to the conclusion that trying to fix the worn spindles and just replacing the nuts is not the best long-term solution. I'm going all in, new spindles, new adjustable nuts, and better adjustable bearings. That's the plan. I've decided not to buy the parts from Proxxon. I've lost faith in their quickly wearing standard M16 shafts, and frankly, they're not the best option anyway. But what really sealed the deal? The fact that I'd be spending €360 on just 3 spindles and 3 nuts. Instead, I'm going with stainless steel trapezoidal spindles and 6 nuts. Add in a rod of cold rolled steel for the nut housings, and the total cost is less than €80. Now, here's a look at the design for the new nuts, along with the spindles and 6 nuts I've already purchased. Time to get to work. I'm starting by making the 3 nut housings. The ones for the Y and Z axes are identical, but the one for the X axis is going to require a little extra work. You know, all that tiring, monotonous and inaccurate hand sawing used to be a pain in the butt, but ever since I built this handy bandsaw, it's become a total breeze. It also saves me from having to hog away tons of material with a roughing end mill. Down the road, I might even make one more modification to it, the ability to use the crosscut fence on the right side of the blade too. Thank goodness for the micro mill. I can just use it to finish these nut blocks without having to reassemble its big brother first. It's also a fantastic real-world test for this little powerhouse. Let's see what it can do with an 8mm carbide 4-flute end mill and cold rolled steel. The nut blocks are ready to go. Now, I just need to get those purchased nuts turned down to size on the lathe. First, I'll put center holes in the spindles. I'm sure that will come in handy later. For this, I'm making an aluminum collet to properly center the shafts and keep them from getting damaged. For the next operations, it's better to use my collet holder. I'll clamp cut off part of a spindle into the 16mm collet and use it as a mandrel for the nuts, which I'll turn to the correct OD. Time to give the first nut housing its hole and thread. Since the position of the hole is quite critical, I'm using my optical center punch. I've converted an obsolete parting tool holder to fit my dial gauge to quickly and easily center workpieces in the 4-jaw chock. Tapping the M20 by one thread is not exactly something I do often, but with the help of my lathe, I can get the start of the thread perfectly straight in the nut. The rest can be cut in the vise. On the mandrel, I'm cutting M20 by 1 external thread on the 3 nuts. One of them will be split later, and those half nuts can then be used to eliminate the backlash. In hindsight, it probably would have been better to clamp the spindle in the aluminium collet. I really had to be careful that the fixed center in the tailstock didn't overheat from the increasing pressure due to the expansion of the shaft. A lot of heat was generated when turning this stainless steel. I really hate this part, loosening the tilting nut on the milling head, because I know that it takes a lot of patience and trouble to get the head perfectly square to the bed. As soon as the drawbar is tightened, that head twists along with it, and that makes for a nasty job. When I built my micromill, I used a completely different principle, and so far, I'm very happy with it. To properly lubricate the spindles later, I'm going to try to add grease fittings with a channel that comes out in the nuts between the fixed and adjustable nuts. In that reservoir, I want to be able to inject oil from the outside. A simple drill hole at a 30-degree angle should do the trick in this case. It's a shame I don't have a nice still picture of it, but this tiny mill had no trouble with this keyway in stainless. I think the rest of the footage speaks for itself. Let's add some music. Well, that's it. A new Z spindle with trapezoidal thread and an adjustable nut for less than a quarter of the cost that the manufacturer asked for. Okay, If I have to factor in my labor, it becomes a whole different story. But with a backlash of roughly 55 microns on the Z-axis and a far more wear-resistant and easy-to-lubricate solution, I'm very satisfied. Now for the X-axis and Y-axis. That's a bit less straightforward, as you'll see in the next video. See you then.